Hi, good evening. I hope you guys are all doing well. My name is Daniela Gonzalez, and today I will be introducing you guys to what is phenylalanine, a comprehensive approach through the lenses of organic chemistry. So basically, what I'm going to be doing today is I'm going to be teaching you guys about the basics of this molecule, this amino acid, while also applying the concepts we have learned in class, as well as discussing some of the future uses of this molecule. I hope you guys really enjoy this. So, why is it important to learn about phenylalanine or organic chemistry in general? I feel like applying organic chemistry and just learning about different organic molecules is very important because it allows you to take what you learn in the classroom and apply it in your daily life. This allows you to polish the material you learn in class and reinforce it will also polish your critical thinking skills. Because, for example, when I first started this assignment, I had no idea what phenylalanine was. But now, after applying the concepts, now I understand that this molecule, its structure, really influences its function, and that this molecule really influences her functioning as well. And this actually has a lot to do with stereochemistry and resonance. And honestly, when you're a student, you think you're never going to use these concepts, but you do. So once again, using these concepts polishes your critical thinking skills, and it allows you to apply what you learn in the classroom outside the classroom. So, uh, let's get right to it. So, phenylalanine, its molecular formula, it's C9H11 and NO2. And as I mentioned, it is an essential alpha amino acid, and we found it in animal products such as meats, fish, and eggs. And some of its physical properties, a really important one is that it is a very unreactive molecule. Um, and that makes it nonpolar, hydrophobic, and insoluble in water. And some other properties I want to mention is that its boiling point is 295 Celsius, and that its melting point is 283 Celsius. And on this side, we have a picture of phenylalanine. So, when it comes to the hybridization, just as a refresher, hybridization it's how the S and P or orbitals of an atom interact with each other and fuse to form bonds. And the way you can find out the hybridization of an atom is by calculating its steric number, which is basically the sum of its pi bonds with any lone pairs. Any steric number with 4 is sp3, a steric number of 3 is sp2, and a steric number of 2 is sp. So, So we're gonna be talking about the hybridization of the specific atoms of phenylalanine. So to start us off, I'm gonna start with the carbons. So in these two blue carbons, we have sp3, and we know that because each carbon is bonded to single bonded to four groups. This one is bonded to two C atoms and two invisible H atoms. So the steric number is 4. We get that because it has 4 pi bonds and no electron pairs. So that makes the steric number 4 and therefore sp3. And the sp3 bond angle is 109.5 and the molecular shape is tetrahedral. Now for this other carbon, it is sp2 and we know that because it has a double bond, double bonds have only one pi bond in a sigma bond. So instead of having 4 pi bonds, we only have 3, so that makes it sp2. And that makes also the bond angle 120 and the molecular shape trigonal planar. And then lastly, oh, something I also want to mention is that this is an alpha carbon. So in amino acids, an alpha carbon refers to a central carbon that that is connected to a carboxyl group in an amino group. So yes, that is the alpha carbon. That's why it's an alpha amino acid. And then lastly, for the rest of the carbons, these are aromatic carbons. And they are aromatic because they're in the benzene ring of the molecule. And they're sp2 because once again they have a double bond. Instead of having 4 pi bonds, we only have 3. So the bond angle is once again 120 and the shape is trigonal planar. Now for the rest of the substituent, we have the nitrogen and these two oxygens. So for nitrogen, You can see it's bonded to two hydrogens, one carbon, and it has one invisible pair of lone pairs. So once we add all of those up, we have three pi bonds and one pair of lone pairs, one lone pair. So the steric number is 4, therefore it's sp3, and once again it's 109.5 in tetrahedral. But now for these two oxygens, this one, as we can see, it doesn't have like, this is very repetitive, but these two have like very unique bond angles and shapes. So this one, we know it's sp2 because of the double bond. So we have like a pi bond and two invisible lone pairs. When we add these up, we get a acidic number of 3, so it is sp2. And it is linear because instead of having just three pi bonds and zero lone pairs, we have one pi bond and two lone pairs, so the molecular shape for it is linear. And the bond angle is 180 because the line is always 180 degrees. And then for this one, we know it's sp3 because we have the two pi bonds and two invisible lone pairs. So the bond angle for that is 105.4. The molecular shape is bent. So for carbons and functional groups, we can always categorize the components of any molecule because once again, it is the atoms that give it a specific function. They make up its identity. So to start identifying them, we're going to start with this side, with the carbons. So then we start off with the arene carbons. Once again, as I mentioned, arene carbons are carbons that are directly on a benzene ring. Then we also have a secondary benzylic and a secondary allylic carbons. What it means to be a secondary carbon is that you're a carbon that is connected to other two carbons. And then what benzylic means is that you're a carbon that is just one bond away from a benzene group, which is what we see right here. And then for what it means to be allylic is that you are a carbon just one step away from a double bond. So, and then we also have a primary vinylic, being a primary carbon means you're a carbon bonded only to one carbon, which is this one. And binylic means you are directly on a double bond, which, yeah, this carbon is on the double bond. And then for functional groups, we have a phenyl group, we have a primary amine. A primary amine is an amine that is bonded to only one carbon and none of its hydrogens have been replaced. And finally, we have carboxylic acid, which is basically just a carboxyl group in a alcohol group bonded to a carbon. And these are the IR spectroscopies of these functional groups, or maybe not the functional groups, but the specific bonds in these functional groups. You have the OH bond of the carboxylic acid, which is right here. And compared to alcohols, this one is much broader. We have the double bonded CC bonds are around 1600 centimeters to negative 1. We also have the CO bond of the carboxylic acid, which would be this section, and it is at around 1300 centimeters to negative 1. And then we also have the CM bond around 1000. Now, for UPAC naming, the reason why UPAC naming is so important is because it allows a chemist to give names to molecules that won't get confused across different languages. So it standardizes naming in molecules, but also telling you a lot of information about the molecule, like the location of its functional groups and some of its properties. So in order to do that, to give a molecule its very own UPAC naming, you have to first find the longest chain of carbons. And then once you find that chain, you need to assign the lowest numbers to the functional groups of highest priority. In this case, the groups with highest priority are the carboxylic acid, then the amine group, and then finally the benzene. So then once we number the chain, which is only 3, the parent name we're going to go for is prop, since it's only 3 carbons, and that's the assigned parent name for 3 carbons. So then at the end, we just add the respective prefixes, suffixes, and numbers of parent name based on these functional groups, and the name we end up getting is 2-amino-3-phenylpropionic acid. Now for resonance, this is a very important concept because earlier on I mentioned why phenylalanine is so reactive. So as you can see here, phenylalanine has a total of 5 resonance forms. And why this happens is because of the benzene group, because the benzene ring, it has alternating double bonds, so that makes it a very stable molecule as the electrons can travel from place to place at any given moment. And the major resonance contributors of phenylalanine are these two, because they have the highest number of full octets and also the least number of atoms with formal charges. But why is this even important? Well, the reason why phenylalanine is unreactive is because, once again, the rotating double bonds make it very easily for the partially negative charge of the resonance hybrid to be spread out. So basically, the benzene group is always happy, like it's never looking for another atom to be fulfilled because its octet is already fulfilled. So that makes it very unreactive. And also because in general CC and CH bonds are very nonpolar and therefore non-reactive. So that makes phenylalanine not want to interact with other molecules. So basically on its own, you can only do so much with phenylalanine, like it doesn't really interact with other molecules. However, it does do this phenomenon called aromatic stacking, in which basically it's kind of similar to hydrogen bonding in the sense that it is a non-covalent attraction with neighboring aromatic rings. Now for chirality, this deals with stereochemistry. So as we can see, phenylalanine has one chiral center, and a chiral center is basically like a carbon connected to four different groups. So then, based on the 2 to the n formula, since we only have n represents the number of chiral centers you have. So since we only have one chiral center, 2 to the 1 is 2. So then we can only have two possible enantiomers for this molecule. And now that we know that we can have enantiomers, we need to assign configuration. And the way we do this is that we need to assign numbers based on priority, which is based on molecular weight. And the lowest priority of these four groups, it has to be placed on a dash bond, which we already have. The hydrogen is the lowest priority, and the highest priority is the amine group. The second one is the carboxylic acid, and then the last one is this R chain, and then finally we have the hydrogen. So once we do that, we're gonna draw an arrow um, connecting 1, 2, and 3. 4, we just kind of ignore it. And since it is counterclockwise, we know this is the S configuration of phenylalanine. So now we have the S configuration, then the only other enantiomer could be the R configuration, which is a mirror image. And it's easy to assume that, oh, they're just mirror images, nothing will really change. But actually, the whole function of the molecule changes depending on what enantiomer you have, because the S configuration is referred to L-phenylalanine in biology, and the R configuration of phenylalanine is referred to as the D-phenylalanine. And once again, the whole function changes because, well, L is natural, D is man-made, and then, well, the L1 is the precursor of neurotransmitters. The D1 is a pain reliever, is used as a pain reliever in medicine. Now, how does our body use phenylalanine? Basically, oxygen molecules in our body are split by this enzyme called PAH, and then this creates a water molecule, and it has an alcohol group to phenylalanine. So in here we don't have anything, and then we have the alcohol group. So this converts phenylalanine into tyrosine, and that is, once we have tyrosine, you can use it to create dopamine and epinephrine and a bunch of other neurotransmitters. So that's why it is why phenylalanine is considered a precursor of these neurotransmitters and why it's so important for our body. But now, when I was researching this, I came across this condition, which is a genetic abnormality by the name of PKU. So basically, what this causes is that genetically, you don't have you have some disruptions in the production of the PAH enzymes. So this leads to seizures, brain damage, and disruptions in development because you're accumulating a lot of phenylalanine. So then, what I propose for the future of the phenylalanine is that perhaps we could analyze this molecule more. so we can find better treatments for this condition. And the conclusion for my presentation is that phenylalanine is an essential amino acid that benefits our health differently depending on the enantiomer, that resonance and types of bonds make an unreactive molecule, and that the functional groups of phenylalanine also play a crucial role in the reaction the molecule undergoes. And these are my references. I hope you guys had a great day. And yes, thank you for coming to my presentation.